Alright everyone, welcome to the fourth MathBytes video in our series on vectors. In the last video, we went over how to use polar coordinates and rectangular coordinates to algebraically represent vectors. And I also said a bunch of stuff like that it's difficult to do vector arithmetic in polar coordinates, but it's much easier to do so in rectangular coordinates. And we use that kind of example of two vectors in polar coordinates, and we saw that we can't just like smash the magnitudes and the angles together, right? And so as a result, that means it's really important to be able to convert back and forth between the two coordinate systems. And so, if a problem gives you a vector by telling you the magnitude and the angle, or in other words, the polar representation, you can convert it to the rectangular coordinate representation so that you can like add or subtract them and do other kinds of vector math on them, right? Similarly, if you know about the components of a vector, but you need to know something about the total magnitude, or like what angle it points at, then you'll have to convert from the rectangular version to the polar representation. And so the main question we're going to work on answering in this video is just how do we convert back and forth between the polar and rectangular coordinate representations of vectors. Okay, so really quickly, just in case you missed the last video or, as a refresher to set up this video here, we're going to quickly kind of talk about what these representations are. And so in the polar representation, remember, we express a vector directly as a magnitude and an angle. In other words, I tell you exactly how long the vector is by telling you what the magnitude is. And I tell you what angle the vector points at, and so you know kind of which direction in space it's going, right? And so using these two pieces of information, the magnitude and angle, for example, if I have a vector like r equals, let's say it's like 3 centimeters long, and it's going at minus 30 degrees. I know that this thing has to be 3 centimeters, 30 degrees below the x-axis, or clockwise from the x-axis. So it's going to look something like this. I know we also kind of glossed over this in the last video, but a negative angle just means clockwise. The usual convention is that a positive value for the angle means counterclockwise from the x-axis, and so negative angles are just going the other direction. Okay, cool. And so with the other representation that we talked about, the rectangular representation, we give the vector by telling you what the x and y components are. And so remember, this first number here is called the x component, and it tells us how far the vector extends in the x direction. And this value here is the y component. And the y component tells us how far the vector sticks out vertically, right? So how far it sticks out up or down. And so the idea is, given these vector components, I can construct the individual parts of the vector and then take the vector sum to figure out the what the total vector looks like. So as a quick example, let's say our vector is this one here, where it has a horizontal component of 3 centimeters and a vertical component of -2 centimeters. And so remember, our usual convention for positives and negatives are that if the value of the component is positive, it sticks either out to the right or it sticks out upwards. And kind of conversely, a negative component either goes down or to the left, depending on if we're talking about vertical or horizontal components. And so in this case, we have a horizontal component of 3 centimeters. So we know that our vector is going to stick out 3 centimeters to the right. And it has a vertical component of -2 centimeters. So it's going to stick out 2 centimeters to sort of in the downwards direction here. And so we then know our total vector looks something like this. Okay, cool. So let's call it there for our refresher and move on to talking about actually converting here. So while it may sound kind of daunting to convert between these coordinate systems, I'd actually be willing to bet that you've kind of done this before. It turns out that these conversions really are just some basic trigonometry, which we should have at least seen before in our math classes. And so let's take a couple of minutes and just do some review of all the trigonometry we'll need to convert between these different coordinate systems. So remember, all of our trigonometry that we know is going to start with a right triangle. And I'm going to label this right triangle to have the 3 sides. So we'll label the hypotenuse H. And then I'm going to label the kind of horizontal side A. And I'll label the vertical side B. And we also have the corresponding angles. So I'm going to call the angle that's opposite to A, angle alpha. And I'm going to call the angle that's opposite to side B, angle beta. Okay, the next thing I'm going to do is just write down our mnemonic device for trigonometric relations. So remember, we have 3 trig relations that we need, sine, cosine, and tangent, and we have this nifty little mnemonic device for them. So we have ka, and toa, right? And remember, this mnemonic device just reminds us that for the sine, we know that the sine of an angle relates the opposite to the hypotenuse. We know the cosine of an angle relates the adjacent side to the hypotenuse. And this reminds us that the tangent of an angle relates the opposite side to the adjacent side. And so remember, these trigonometric relations take an angle as an input, and they give you a fraction as an output. And these fractions that they spit out are the ratios of different sides of the triangle. So remember that if you take the sine of an angle, the output of a sine is going to be the ratio of the opposite side to the hypotenuse, where the opposite side is kind of the side opposite to the angle we've picked out here. For the cosine, using our SOHCAHTOA mnemonic device, we know that this is going to be the ratio of the adjacent side to the hypotenuse. And finally, the tangent of an angle theta is going to relate the opposite side to the angle to the adjacent side to the angle. And so let's take a second here and just kind of write all these out in terms of this particular right triangle we've drawn here. So I'm going to label this right angle here. And let's do sine of alpha. Let's do cosine of alpha, and let's do tangent of alpha to start with. And so if I take a look at sine of alpha, right, I can see alpha is this angle here in the top right. And so I know that this is going to relate the opposite side to the angle to the hypotenuse, right? So I know the hypotenuse of this triangle is the longest side, and that's going to be this h here. And if I take a look at alpha, the side of the triangle that's across from it is the side labeled A in red, right? And so then sine of the angle alpha is just going to tell me the ratio between A and H here. If I do the same for cosine, right, cosine of alpha is going to be the relationship between the adjacent side and the hypotenuse, and the side of the triangle that's adjacent to A is the blue B side, right? And the hypotenuse is still H here. And finally, let's think about the tangent of the angle really quick. Tangent of alpha is going to relate the opposite to the adjacent side, right? And so the side that's opposite alpha is once again this side in red, A. And the adjacent side is the blue side, which is B, like this. And so then, right, if I want to know what the sine, cosine, and tangent are, I can kind of construct those for this alpha here. If I do the same for beta, we'll see that we get slightly different answers because beta is a different angle, right? And so the opposite adjacent the opposite and the adjacent sides are now different sides. So specifically, if we take a look at this angle beta in the bottom left of this triangle, it's still the ratio of the side opposite to beta with a hypotenuse. But now the side opposite to beta isn't A like it was before. It's now going to be B, right? And so we see that because the angle that we're looking at changed, the angle we've picked out is a different one, then the kind of opposite and adjacent sides will switch here. Similarly, if I write the cosine of beta, this is going to be the adjacent side to beta, which is now side A, divided by the hypotenuse h. And finally, the tangent of beta is going to be the relationship between the opposite side of beta to the adjacent side of beta, which in this case is b over a. And so we can see kind of a pattern here. If we switch the angle that we're looking at, right, the definitions of the sine and cosine will kind of swap around like this. So sine of alpha is the same as cosine of beta, and cosine of alpha is the same as sine of beta. And this thing happens with tangent, where tangent of alpha is the reciprocal of tangent of beta. Okay, and so there's one last right triangle theorem that's going to be useful here, and that's going to be the Pythagorean theorem, right? So there's one more thing we know about this triangle, and it's that the hypotenuse squared is going to be equal to the sum of the two legs squared, a squared and b squared, like so. And we'll see why this is useful later on when we're doing our coordinate conversions. Okay, we've just done like a ton of trigonometry, right? And you may be thinking, I am about to click on this video of Gordon Ramsay swearing at people. Why the hell are we talking about trigonometry? But don't click off yet. I swear we are about to get there. Okay, cool. So we need to know why this is relevant for vectors, right? And so it turns out to be the case that the two representations of vectors that we use really just label different parts of a right triangle. So what I mean is, let's consider the polar and rectangular representations of a vector, right? Where we have a vector r that might look like this, And we can express it in one of two ways. We can either say what the angle and the magnitude are, or we can tell what the components are. And so what I can do is take the same vector, and I'm going to label it a few different ways. First, the polar representation tells us what the length of the vector is, and the angular part tells us what angle it makes with the x-axis, like this, right? And then what I can do is also label the components of this vector. So we also know that if I project this vector onto the x-axis, that gives us an x component that looks like this, and the y component of this vector looks like this. And you may be kind of seeing where we're going with this, right? Each of these representations really just labels two out of kind of the four important parts of a right triangle. And we also know this is a right triangle, right? Because we know that the x and y components are always perpendicular to each other because x and y are always at 90 degrees, right? This is one of the benefits of having what's called an orthogonal basis, in which the kind of ways we break down space are perpendicular, right? What I'm also going to do is label this other angle here as theta c, or theta complement, because whatever angle theta is, right, this angle is 90 degrees minus that one. Okay, so let's go through really quickly and write the same trig relationships using our SOHCAHTOA kind of mnemonic device, just so we can see how these kind of different body parts of the vectors are related to each other. And so let's start by doing sine, cosine, and tangent of this green angle here. So let's do sine of theta. And we know the sine of the polar angle is going to be the opposite side to the theta and the hypotenuse, right? So we know this is going to be side ry divided by the total hypotenuse length, which in this case is r. And cosine of theta, oops, let me do that in green so it's nice and color-coded. Cosine of theta is going to be the ratio of the adjacent side to theta over the hypotenuse. So the adjacent side in this case is rx, right? And the hypotenuse is, once again, the total magnitude r. And finally, the tangent is going to be the ratio of the opposite side to the adjacent side. In this case, the opposite side to theta is going to be ry, and the adjacent side is rx. And so we see that these relationships, right, if we know r and we know theta, and so we can see from these trig relations that if I give you the polar representation in terms of r and theta, you can always solve for the unknown ry or the unknown rx. And so the idea is if you know the polar representation, you can use these trig relations to solve for the x and y components. And so just for kind of completeness, I'm going to write down these same relations, but instead we're going to look at the complementary angle, theta complement. And so like we saw before, right, if we switch the angle that we're looking at, then the sine and cosine kind of swap around. So let me set this up really quick. And right, the sine of theta complement relates the opposite side to the hypotenuse, which is rx, and the hypotenuse, which is r. And the cosine of the complementary angle is going to relate the adjacent side, ry, to the hypotenuse, which is the total magnitude. And we see once again that these, that because we're switching the angle that we're looking at, right, these ratios kind of flip-flop like so. Okay, and finally, as we saw before, the tangent of the complementary angle is going to be the reciprocal of the original tangent, right? So in this case, if I take a look at theta c here on the top right, the opposite side to theta c is now rx, and the adjacent side to theta c is ry. And so this is kind of the complete set of trigonometric relationships that relate the variables that are involved in the polar and rectangular representations. And so finally, the last kind of formula that we'll need here is not a trig one, but we'll just write down the Pythagorean theorem again. The horizontal and vertical legs, rx and ry squared, by the Pythagorean theorem, we know have to be related to the hypotenuse, r squared. And so this is useful because, for example, if you know the rectangular representation, you know rx and ry, and this formula lets you solve for what the magnitude must be if you want to convert it to polar coordinates. And so as we can see, right, the trig relations are really useful here because they're this huge pile of relationships that we can use to relate the unknown parts of the triangle to our known parts of the triangle. And so the key fact here is that as long as you have any two of these parts, you can always infer the last parts of the triangle that you care about. Like I said before, right, if we know r and theta, we can solve for rx and ry. If we know Rx and Ry, well, then we can use like this relationship and this relationship to solve for the hypotenuse R, or in other words, the magnitude R, and we can solve for the angle theta, right? And so that's a lot of math to look at, right? So it could be useful to kind of summarize this into a compactified method for doing these conversions. And so let's write out kind of 4 steps that we can do. First, I think it's always useful to draw the vector out so you can visualize how the different sides are related to each other. Then the second thing I like to do when I'm converting between polar and rectangular is just to label all the components. So in terms of kind of this diagram on the left-hand side, right, I do things like label the hypotenuse, label the angles, and label the x and y components here. Then the next thing you want to do here is identifying all the known values. So in this case, right, what I mean is like if I give you the rectangular representation, then you can just label the x and y components with like the specific numbers I gave you or something like that. And then the last thing we need to do is identify the equations that relate the known variables to the unknown variables. So I'm going to compact this down a little bit and just say identify useful trig relations. And all that really amounts to doing is kind of picking out the trig relations for which you know 2 of the variables and don't know the third. And then you can solve those equations for whatever third unknown variable you need. Okay, I think it would be pretty irresponsible to make you think about all this math and not do a couple example problems. So here's what we'll do. Let's do one of each conversion for this video, just so that we can kind of get a flavor for how this is done. So first, let's think about converting from polar coordinates to rectangular coordinates, right? And so step 1 is going to be draw a vector. And so my vector is about 10 centimeters long. It is at 60 degrees from the counterclockwise from the positive x-axis, right? So that's going to look something like this. I can label my vector like so. And then the next step is going to be drawing the other components. In this case, right, I've given you the polar representation, and so I should draw the other components for the rectangular one, which is going to look like this. Oh, that is not the right length. We'll just assume these touch. This is a little sloppy, but let's make sure to label these as well in a nice color-coded way. This is Rx. Okay, great. Then we can identify the 2 knowns. In this case, right, we know the hypotenuse and the angle, which I've already labeled here in purple and green. And finally, I need to identify the trig relations that relate the 2 known variables to the unknowns, right? So in this case, let me just catch up really quick. Identify useful trig relations. Okay, by experience, I can tell you the useful relationships here are going to be the ones that relate things to the hypotenuse. So in this case, it's going to be the sine and the cosine. So I can do sine of 60 degrees gives me the relationship between the opposite side to the 60 degrees, right? So the opposite side to this angle that I've labeled here is going to be Ry. And the hypotenuse is 10 centimeters. And the other relationship I can use here is the cosine relationship, which relates the adjacent side to the hypotenuse, right? And so the adjacent side here to this green angle here is going to be the x component, Rx, and the hypotenuse is still 10 centimeters. Okay, great. And so we can see here, right, on the left-hand sides, I've got the sine of 60 and the cosine of 60. And both of those are things that I can plug into a calculator. So I'm going to do that really quick. And we find that the sine of 60 degrees is 0.866. And that's equal to Ry over 10 centimeters, right? So what that means is I can solve for Ry here, and I find that Ry is then equal to the hypotenuse, which is 10, times sine of 60, which turns out to be 10 times 0.866 is 8.66 centimeters approximately, right? And similarly, right, I can see that cosine of 60 is another thing I could plug into a calculator, and it turns out this one is 0.5, exactly 1/2. And so then I can just solve for Rx by multiplying both sides by 10 centimeters, and I find that Rx is equal to 10 times sine, 10 times cosine of 60, which is 10 times a half, which is 5 centimeters. And so then I can collect these together and write down the rectangular representation of this vector. R in rectangular coordinates is, the x component is 5 centimeters, and the y component is 8.66 centimeters. And so we can see an example of, right, using our trig relation, sine and cosine, to solve for the x and y components here. Okay, perfect. Let's move on to our next example, going from rectangular coordinates to polar coordinates. So let's say I have a rectangular representation of a vector with an x component of 3 centimeters. So let me just draw this vector really quick. X component of 3 and a y component of 4. It's going to look something like this. It's a little short, but that's probably fine. All we need is that this is kind of like to scale, but it doesn't have to exactly be to scale. So this is about 3 centimeters. Okay, and so the full vector looks something like this, right? This vector currently has some unknown length v, and it has some unknown angle theta with respect to the positive x-axis. And so once again, our goal is going to be to find these two unknowns, right? And we're given 2 of the 4 body parts of this triangle. And so now what we need to do is figure out how to get the 2 unknowns using our trig relations. And so first what I can recognize is that I have both of the legs of the right triangle. And so the easiest thing to do first is use the Pythagorean theorem to find what the hypotenuse of this triangle is, right? And so by the Pythagorean theorem, right, we know the hypotenuse squared must be equal to the square of the x component, vx squared, plus the square of the y component, vy squared. If I fill those in for my problem here, this is going to be 3 squared and 4 squared. And of course, 3 and 4 are our favorite numbers for right triangles because they form a Pythagorean triple. This is going to be 9 plus 16, which is, of course, 25. And so now I know that the hypotenuse squared is 25, which immediately tells me that then the hypotenuse v must be 5 centimeters. Sweet. Okay, now what I have to do, now the next thing I have to do is figure out what the angle theta is, right? What this green angle in the bottom left is. And so if I take a look at theta, I can recognize that maybe the easiest thing to do here is recognize that I have the opposite and the adjacent sides already, right? And so what that means is because I have the opposite and adjacent sides, I want to use the trig function that relates those two. And thinking back to our SOHCAHTOA mnemonic, right, that's going to be our tangent. Because tangent of theta relates the opposite to the adjacent here, right? And so filling in the opposite and adjacent with this actual triangle, right, the opposite side to this green angle theta is going to be the 4 centimeter long side, which is Vy, and the adjacent side to this angle theta is going to be the x component, Vx. And so filling in the actual values from this triangle, right, we know Vy is going to be 4, and Vx is going to be 3. And so now my equation looks like tangent of theta equals 4/3. And so if I need to get what's on the inside of the tangent, right, I need to apply the inverse tangent to both sides. In other words, I need to kind of like crack open this tangent, like so. And this is going to be the inverse tangent of 4/3. And so on the left-hand side here, right, algebraically, what's going to happen is the inverse tangent is going to undo the tangent. And what we're left with is just theta on the left-hand side. And I can plug in the right-hand side into a calculator, right? The calculator will tell me what the inverse tangent of 4/3 is in degrees. And so after plugging this into a calculator, you should find that the inverse tangent of 4/3 is about 53.1 degrees. And we'll leave it there at kind of that precision. Great, and so now that we have the hypotenuse and the angle, I can write down the polar representation. V in polar is going to be given by r comma theta, or v comma theta, excuse me, which is 5 centimeters. at an angle of about 53.1 degrees. Okay, so I think that's probably enough for this video. As per usual, let's move on to a summary for what we talked about today. So there's really two key points that I want you to take away from this video. First, it's that polar and rectangular coordinates label different parts of a right triangle created by the vector that we're looking at, right? And so in other words, what I mean is given some vector v, like we saw here, the length of the vector is really just the magnitude given by the polar representation, right? And the angle is this angle here made relative to the horizontal. And so we can see that this really just tells us what the angle of the right triangle and the hypotenuse are, and the components of the vector tell us what the horizontal and vertical legs of our right triangle are, right? So this is Vx, and this is Vy. The reason we know this has to be a right triangle, once again, is because we start with an orthogonal basis. In other words, we know that x and y are perpendicular to each other, right? So there's always going to be a right angle here between the components. The second thing we saw was that we can use trigonometric relationships that involve the known components to solve for the unknown components, right? We had that four-step process that involved looking at the knowns and unknowns, right? And picking out the trigonometric relations that relate the two knowns to the kind of other coordinates that we want. And so just to summarize that four-step process, we want to start by drawing the vector like we did up above right here. Then the next thing we want to do is label the components, which amounts to kind of labeling the legs of the triangle, the hypotenuse and the angle, right? Then the next thing that we want to do is identify the knowns, so we can label the exact values that the whatever problem gives us. And then the last thing we want to do is, based on the knowns and unknowns, like basically what we're converting from and what we're converting to, we want to identify the trig relations that involve two known variables and one unknown variable. And we wrote that down earlier as just identify useful trig relations. And that way we can just solve for the single unknown in each of the kind of trig relations we pick out. And so the last thing I want to say before I let you all go is that this exercise of going from polar to rectangular coordinates and conversely, right, from rectangular to polar coordinates is something that you're going to do like 1,000 times in basically every physics class you take. It's a really, really important thing. And so as you do it more and more in these classes, you're going to develop kind of a fast intuition for these. And I wanted to kind of summarize a couple quick formulas that will be useful as you get faster and faster. So what I've done here is, once again, I've kind of like given the right triangle and labeled all the components here. And I just wanted to write some quick formulas for how we can get the different coordinates based on the given coordinate system. And so up here in the top right, you can kind of use these formulas to convert quickly from rectangular to polar. First, given the x and y components, we know that the magnitude of the vector is really just the hypotenuse, right? And so very quickly we can write down that we know rx squared plus ry squared, and the square root of that is going to tell us what the magnitude of the vector is. Similarly, we know that, like we saw in our example problem, right, we can get the angle by using the tangent relation, and the kind of final formula we arrived at was that the angle theta is going to be the inverse tangent of the opposite side to the adjacent side, ry over rx. Like so. If for some reason you're interested in the complementary angle, theta c, then right, the opposite and adjacent just kind of switch places. And so now the opposite side is rx, and the adjacent side is ry. And so on the flip side, if we want to go from polar to rectangular, or in other words, given the purple hypotenuse and the green angle here, we can write down some formulas for quickly picking out the x and y components, right? And so for the x component, right, we saw earlier that the x component forms the kind of adjacent side to the green angle here. And so our final formula, if we do this just fully algebraically, is that the x component is going to be related to the cosine, and it's specifically going to be r times cosine of the green angle theta. And ry is going to be the opposite side here, right? So it's going to be the sine relationship, and we're going to have ry equals r times sine of theta. And for completeness, we can also write this in terms of the complementary angle. And so remember, when we're looking at the complementary angle, basically the sine and the cosine switch places, right? And so we can kind of very quickly write down the results in terms of the complementary angle here. This cosine becomes a sine. And so now we have, Oops, this should be in black. And now we have our x is r times sine of theta complement, and our y is going to be r times cosine of theta complement. And we see here, right, these cosines and sines switch around. If you don't believe me, it's a really good exercise to just work these out from scratch, but this is kind of a useful little cheat sheet for when you need to do this really quickly for a bunch of homework problems or something like that. Okay, that's probably enough time spent doing trigonometry today, right? As per usual, if you have any thoughts or questions you want to share, please leave those in the comments down below and I'll try to get to them. Next time, we're going to be working on kind of the last part of our vector series, where we're going to be talking about how to actually do, finally, algebraic vector addition, subtraction, and scalar multiplication. So we'll kind of bring it all together and cap off the rest of the skills we'll need to do vector stuff in intro physics. And finally, please don't forget to like and subscribe for more free physics problem solving tips. This has been Physics Tutoring Quantized.